Hi, so in this video, I wanted to just go through a quick example of a weak base equilibria. This video is going to be really short just because honestly, the ideas behind how we handle like weak bases are very similar to what we do with weak acids, right? It's just like a slightly different equation, a slightly different K constant associated with it. But as far as the like basic concepts go, it's very much the same as what we've covered earlier in the chapter. But so here I have an example where I have a solution of ammonia or NH3. NH3 is like one of our quintessential weak bases. It's like kind of the go-to as a weak base example. And so it has a Kb, again, a base dissociation constant of 1.76 times 10 to the minus 5. And so I want us to find the pH of a 1.0 molar NH3 solution using this information. Now, before we dive into all of it, because this is, again, like a lot of stuff that is really just the same ideas, just kind of packaged in a new way, I want you to pause here and think about how you could solve this problem without any real guidance. I give you a hint here on, what the base ionization reactions may look like, right? That's the equilibrium of interest here. So you might want to go back into your notes, you'll find like the generic equilibrium associated with a Kb and use that. But here I want us to practice, finding the pH of a basic solution, right? So again, kind of similar to examples that we've done with acids, but just in a slightly new way. So go ahead and pause, take some time to think about this, and then I'll discuss in a moment. Okay, so hopefully you've taken some time to think this one through. For one, even if you weren't totally sure about how to approach this problem, right, as like a general guess here, because we're working with a base, right, we can kind of narrow down our options as far as like this multiple choice problem goes based off of, what we know about basic solutions. Remember that for an acidic solution, the pH is expected to be less than 7 or even like a negative number. For basic solutions, we should have a pH that is greater than 7. So right off the bat, I can kind of narrow things down and say, okay, A and B probably don't really make sense for this particular problem. And so my instinct initially is either C or D. In this case, with this 1 molar ammonia solution, it is in fact D as the answer, 11.62 as our pH. Now to show exactly how we get to that point, right, we're again going to start by first looking at the base ionization or base dissociation reaction for ammonia, which as a general rule, bases kind of have the following format for their reactions. We have our base reacting with water to then form hydroxide as well as the conjugate acid of the base. So that's shown right here at the top of my ice table, right? I have NH3 plus H2O producing OH minus and NH4 plus. Now, in terms of setting up this ice table, it's going to go exactly the same as we always set up our different ice tables, right? We have our initial concentration of the NH3 as 1.0. We don't have initial concentrations of anything else given, so we assume that those are 0. We can only add to the product side because they start at 0, and so we have plus X on the products, minus X for the reactants. And if we look at our Kb constant, which we're given here, right, that Kb goes with this equilibrium, and it's pretty small compared to our 1.0 molar of NH3. So that means then that the equilibrium concentration of ammonia is going to basically stay at 1.0. So that minus X to it basically doesn't matter. Now again, going through the same process that we generally do for these equilibrium problems. We have a Kb constant. We can write out the Kb expression in terms of concentrations. Always it's just the products over the reactants. As a reminder, for the water here, because it's a pure liquid, it doesn't show up in the equilibrium constant at all, and so we have then just concentration of OH times the concentration of NH4 plus divided by the concentration of NH3, which when we apply our ice table and the Kb value that's given to us, we can basically solve for this very simply algebraically, find that the value of X is equal to 0.0042 basically. And so this X value right here, right, this is both our concentration of NH4 plus and OH minus. It's the OH minus that we're interested in here though, because we're trying to find pH. Now kind of my quickest way to find pH when I have a hydroxide concentration is to first find the pOH. So basically just taking the minus log of that OH minus concentration. What I find from that is a pOH of 2.38 basically. And again, the relationship between pH and pOH is just that they should sum up to 14. So that's to say that the pH is equal to 14 minus whatever our pOH is. So I take 14 minus 2.38, and I get then 11.62. So again, that's how I can find the pH of a weak base solution. And the process behind this is very similar to what we do with an acid equilibria. There's just a slight distinction between like what does an acid dissociation reaction look like, what does a base dissociation reaction look like. It's really important to recognize those patterns and kind of have the generic format down so that you're able to work with both of them. But please let me know if you have any questions, and I'm always happy to help. Bye.